This meeting is being recorded.
Very well. Okay, good afternoon, everyone. Before we start, are there any questions that I can answer? Remarks or anything here online? Okay. So we have 2 more lectures to go. On Wednesday, I have office hours as usual, but in light of the exam being recent and there being one more assignment, I will hold longer office hours. So if anybody wants to come to check like the exams answers and stuff like that, then I'll be probably extending my office hours by about an hour or so to kind of answer people's questions. However, and I will reiterate this on Wednesday, if the usual time I end is 4:30, I think. Don't be like, oh, it's an extra hour and turn up like 5:30. Being there, do let me know if you cannot make it to the regular time, okay? So that I don't wait there for an hour and for nobody to turn up. But I will update the details on that. Okay, so last time we kind of left the safety net of recursion based on data templates, right? So templates that we use for data definitions, recursive data definitions, where the template dictated that each recursive call is on a value that's strictly smaller than the previous one, and it was smaller exactly by peeling off one level of the self-references, right? So in case of lists, the template would dictate your recursive call is always on the rest of the list, right? You drop the first element and your recursive call is on the first of the list, which is quite a powerful notion, but it doesn't cover all the possible problems that we might want to solve. And the problem that we started with last time was splitting up a file where file is just represented as a list of chunks, where a chunk is either a string or a new line. And we wanted to split the file into a list of lines based on the new lines, right? So even though we are dealing with a self-referencing or self-referential or recursive data type, which is a list, the recursion pattern dictated by the template for list doesn't fit our problem, right? So we had to look for other ways of splitting up the problem into different parts. And what we ended up with is one main function, file to lines, where we had a base case where an empty file would yield an empty list of lines, so there are no lines to return. But in the non-empty case, instead of calling our function recursively on the rest of the file, we needed to use a different function to reduce the problem, right? So what we ended up with is simply taking the first line of the file and calling recursively on the rest of the file, where the rest of the file is defined as everything but the first line, right? And because this call isn't on the immediate rest of the list, right? So it's something where multiple elements might be dropped. It complicated our argument about termination a little bit more. We have two helper functions, and the termination of our file to lines function depended on both of these functions. A, that they terminate, and B, that they return a result that makes the main function terminate, right? The termination argument for both of them is relatively simple because they are both based on the list template. So we either have the empty file. If we have the empty file, we terminate. So that's that. Otherwise, if we have a non-empty file, if we find a new line, we terminate early here. Otherwise, we have a recursive call, but the recursive call is on the rest of the file. So we have a decreasing argument. In the other function where we are dropping the first line of the file, again, if the file is empty, return an empty list. We terminate. That's fine. If the list is non-empty, we again either terminate early and return the rest of the list, or we have a recursive call that is on a smaller argument, just by given by the rest. So they both terminate, so that's good. But that didn't finish our argument, right? Because, and I did a little example here. So if I would just forget to return the rest of the file here, right? It wouldn't be any more true that this function returns a strictly smaller result, right? It wouldn't be true that in all cases, either we get an empty result, or if there is something, then we drop something from the front of the list, right? In the case where we would have a new line as the first argument, we would return the same thing, and the recursive call on file to lines wouldn't be on a decreasing argument, and we would not terminate. So the important thing here is, A, both of our functions terminate. B, whatever we use to reduce the problem needs to actually reduce the problem in each case. Okay, so that complicates a little bit. However, this approach is slightly more general, because if you just imagine this function being replaced by rest, we get the same thing. Rest just happens to always guarantee to return a smaller argument. Okay. Any questions from this example about this example from last time? I think it should be okay. Now, as I said, we kind of left the safe confines of using a recursive data type and recursion based on that, and we have a slightly more general case. We do, however, have a bit of a recipe and a bit of a template to deal with these problems. The template or the recipe isn't just as good or as rigid as the one that we used for data types and self-referencing data types. The basic approach is to think of the data that we are processing as an encoding of a problem and not just as a data type itself, right? What I mean here, we don't look at data, for example, a list of elements as just being like, well, it's either empty or it's non-empty and it carries some information. We think about it, how do we want to use it, right? What does it represent? What is the problem that we are trying to solve? And by looking at our data as an encoding of a problem, we hopefully will be able to answer some questions about that. And that is about what are the trivial cases and what are the trivial answers that we want for those. How do we divide the larger problem into a sub-problem, and how do we solve that sub-problem? Okay? And then our argument about termination goes from just thinking about the single function into thinking about the overall algorithm and how the functions interact and what do they return? How do they allow us to reduce the problem as we go further? Okay? So this leads us to a bit of a design template for generative recursion, and that is Based on this analysis of our problem, we need to observe, okay, we must have at least one case where the recursion stops, right? The base case. In our file to lines example, it was the empty file. That's where it just stopped. So that gives us the base cases, right? Those are the trivial cases, and we need a solution for that. What do we return? File to lines, just return the empty file, empty list of lines. Then we have usually at least one case with recursion, right? Where we need to think about, okay, first of course we need to identify when that applies. So what is our predicate that we use in cont? But we also need two pieces of code. One is a function that will generate the input for the recursive call. And this is where the name generative recursion comes from. Because in each recursive call, we have some sort of generator of a subproblem, right? And once we compute that, we have our recursive call, and then we need a function or a piece of code that uses the result of the recursive call to compute the final result, okay? So in our case, again, coming back to this, take first line is the generator of the smaller input, right? So that's where we have the recursive call. I'm pointing to the wrong file, this one. Drop first line is our generator. Once we have the recursive call on that, the result is then combined. It is not explicit here as a separate function, but it's combined using the expression const take first line, right? So we combine the result with the result from there, and we return it. Okay, so we have our generator and we have our combiner of the result. And this leads us to something like a template for these generative recursive functions, or also general recursive functions, right? We have a set of trivial cases where we run a trivial solution. Any kind of expression can be expressed as simply a function of the current input. And then we have one or more complex cases where we have recursive calls on smaller problems that are generated according to some function or expression, and we combine the results of those. Okay. So we need to identify what are the trivial cases looking at the problem that we are trying to solve, what are the trivial solutions for those, then what are the complex cases where we do need to split up the problem into subproblems, solve them, and combine them. Okay. This approach generally is something that we call divide and conquer. I don't know if anybody heard this term in relation to algorithms. You take a problem, you divide it into subproblems, solve those subproblems, and combine them together. Okay, so generative recursion is an embodiment of a divide and conquer approach. Any questions about this? Kind of general, higher level. Okay. So, as with files to lines, file to lines, some problems actually kind of dictate the generative recursive solution, because our using just the template doesn't really cut it. However, some problems call for might have a simple solution using the data template, which might not be as efficient as another solution where we use a little bit of domain knowledge about the problem to actually split up the problem in a different way rather than just chipping away little pieces of it. Okay, and to exemplify this, let's write a function which given a number x and a natural number n, computes the nth power of x. Okay, so we want a function nth power which takes a number and a natural and returns a natural, and we will use the if you remember, at one point we defined a recursive definition for naturals of where a net is either 0 or it's at 1 to a natural. Okay. Let me x n. So I won't be writing the template out here. I will just write an inline template here. So we have two cases for natural numbers. Either we have a 0, we do something, or we have a positive case where we have a recursive call on a smaller number. Right? Now, what do we return in each of these cases? If n is 0, what is the result? Yeah? Just 1. Easy. If it's non-zero, positive number. Yeah? Exactly. We just multiply x with the smaller power, right? This expresses the fact that x to the power of 0 is 1, and x to the power of n plus 1 is x times x to the power of n, right? Let me do some examples. Anything to the power of 0 is 1. Number itself. And because I only remember powers of 2, let's try this one. Tests out fine. So we have a pretty simple exponent function or power function following the template that comes with the net data type. However, can we do better performance-wise here? Right? If I try this function on relatively small numbers, it runs relatively okay, but it starts registering some time spent there. If I try to calculate the power of 2 to 100,000, it will not only take some time to print it, but it will take some noticeable time to actually calculate the power, right? It's a long number. It's a very long number. So 2 to the power to 100,000 yields a result in roughly 1.5 seconds here. Now the question is, where does this time come from? How many steps are we performing? How many multiplication are we performing when calculating a power using this function? Yeah? N steps, exactly, because every time we have an n, we have a recursive call that multiplies x by the result of 1 less n, so the performance of this function is actually linear in n, right? Which is the power. And I think I said at some point that linear is very good in most cases. But in this case, we can do better. Any idea how we can do better? Exploiting some properties of powers that allow us to take a different approach into splitting up the problem, right? Here the only way, the way we split up the problem is simply make the problem one less. Josh? Uh-huh. I'm not sure I follow. What's that? So help me a little bit. So if I have 2 to the power of, or x to the power of n, what needs to hold for n for this to be applicable? We might be thinking about the same thing. I think, yeah? Exactly. If it's odd, exactly. So there's a difference between when the number n is even and when it's odd. Charlie?
Yeah, so because we know that any even number is just 2n and the odd number is 2n plus 1,
Uh-huh.
we can arbitrarily split that into like 2 cases. One where you have the even number and you just divide it in half and calculate both of those halves, and one where you have an odd number where you can subtract 1 and then do the even case.
Yeah, exactly. So we have 2 cases for even, right? Either n is even, and then any x to the power of n can be expressed as x to the power of 2m for some m, arbitrary, right? And then we can use the fact that this is exactly as raising x to the power of m and then raising that to the power of 2, or times, in other words, right? And if it's odd, then all we need to do is to reduce n to be even, which is just, well, then this must be 2m plus 1 for some m, which means that it's the same as multiplying x by x to the power of 2m, which then is the same as multiplying x to the two, right? So we have 2 cases here. All we need to do is to, in the even case, right, and it basically covers everything because odd can be reduced to the even case very easily. In the even case, all we need to do is to raise x to m, where m is actually half of the original number, right? So the performance of this part will be just x to the power of m plus 1 more multiplication that we do here. Okay. So let's try to use this approach. to define, and let's call it better. Still takes a number and a nat and returns a nat. Okay. So now instead the zero case and the positive case, we will have an even case and an odd case based on our analysis. So here we just want to calculate x divided by 2, and we want to square that. Yeah?
We also need a zero case.
Exactly. That's the one that I ignored in my analysis. We actually need a zero case, okay, which is still 1. So well spotted. And in this case, this is minus n1 times x. And we're good. If we wanted to, we can expand this one and say it's the same as this. Right? But if we skip that, that's okay, because this corresponds to the immediate recursive call. Okay, let's make sure that this works. And it does. Now, what is the performance characteristic of this one in terms of n? Charlie? Exactly, it's log base 2 of n, because in each recursive call we are basically halving the problem, right? We start with, I don't know, n to the 2 to the power of 8. It's even, so the next time we call this, we call it with n being 4, right? Next time n being 2, next time n being 1, which is then odd, so we just remove 1 and we hit the zero case. Right, so each time we are halving the problem instead of just taking away 1 and going down through that one. What does it look like in practice? So the original function took about 1.5 minutes, I think, to compute. 1.7. Now the new one just a little bit more. The new one barely registers, right? 1 millisecond compared to 1500 more. Right? So that's quite an impactful optimization, doing a linear kind of performance on just like chipping away one after the other, which is relatively clear and nice. But if we exploit our domain knowledge about the problem, about the function that we are trying to write over the data type, we can have more efficient ways of splitting up our problems into subproblems, right? And this allows us to improve performance quite a lot. So this one is roughly log 2 of n steps on this one. Any questions about this example? And again, in terms of termination, where our original argument was relatively straightforward, right? We either have, if we have a natural number which is either 0 or it's some positive number, we either hit the base case, in which case we immediately terminate, or we have a positive case where the function is called recursively on a problem that is one smaller, which means if we keep chipping away, we will eventually hit the 0 case and we will terminate. Here it gets a slightly more complicated, so we again have the 0 case, but we have two cases here, right? So if we have an even number, we have the problem, so we have a recursive call on a smaller problem. We also need to argue here that because we have an even number, then dividing that number by 2 gives us a natural number again. So we have a smaller number and it's a natural number. That's important here. In the odd case, we basically just chip away 1, reduce the number to an even number, and the same argument applies here, right? So this function satisfactorily terminates, provided that we pass it a natural number. Okay. So if there aren't any issues with this, let's do one more example of exploiting the domain knowledge to improve performance of algorithms slightly better. Does everybody know insertion sort? Have you heard about insertion sort as a simple sorting algorithm? Okay, let's try to implement a sorting function. So design a function that, given a list of numbers, the list in, let's say, in ascending there, according to less than as the order on the numbers. So let me call this function sort this. Given a list of number returns a list of number. Let's say something like this. And what I'd expect back is 1, 2, 3 is twice, 4, 6, and 7, if I'm not mistaken. And I have 8 as well. 1, 2, 3, 4, 5, 6, 7, 8. Yes, okay. So, and let's design this function using the list template, since insertion sort is something that actually falls out quite nicely out of that. So we either have an empty list or we have a non-empty list. In the non-empty case, we have the first element, and we have a recursive call on the rest of the list. Okay. What do we return for the empty list? Charlie?
Empty.
Empty, nothing to sort there. Sorry?
Because we're building another list. We want to keep the
Mm-hmm. Okay. What about the recursive case? So what I know about this is if I implemented my function correctly, what this should return is a sorted version of the rest of the list, right? So the idea with insertion sort is all I have to do now is just take the first element and find its appropriate place in the sorted rest of the list. So I might need some help here from a helper. So I just insert my first element into the list at an appropriate place. So if I, for example, have a stack of cards with numbers on them, right? I pick the first one, insert it into the empty list, which is already sorted. I now have a list of 1 that is sorted. I pick the second card and I decide either I put it onto the first card or below the first card. Then if I take the third one, I have to decide, do I put it onto the first one, in between those two, or under the second one, etc. Right? So it again corresponds to basically having a stack of things and trying to sort them. Where was I? Right, we were implementing insert. Let's do it as a local definition. I want insert that takes a number and a list of numbers and returns a list of number and does the following: given a number and a sorted list of numbers, insert according to less than as the order. Define, insert, and list. Again, we can use the list template for this. We have the empty case, and we have the cons case, in which case we have the first, and okay. So if I have a number and an empty list, what do I get back? Finn? A list with just the number, right? An empty list is trivially sorted. A new list will be still trivially sorted if I just, cons, if I just return a list containing just the one element, right? Okay, how about the cons case? I have a number, I have the first of the list, and I have the rest of the list. What do I need to do? Where does the number go, yeah? So I need to distinguish between two cases, right? And this tells me where the number n will go. Either n is smaller than the first, or it's not. If it's smaller, what do I do? Yeah? Exactly. If n is smaller, that means that its spot is at the front of the list, right? Because if this list is sorted, that means that the smallest element is the first element, and if n is even smaller than the smallest element, then n needs to be at the front. And I'm done there. Otherwise, the smallest element of the list still needs to be the first here, and I still need to find an appropriate spot for n. as many parentheses here. Okay, so this is insertion sort. Whenever I have a non-empty list, take the first element and insert it into a sorted version of the rest. I insert the number depending on, well, if the list is empty, then the result must be the list containing just the one number, right? L is empty in this case, so it's just a singleton list. Otherwise, I need to compare the first element to the current number. If the number is smaller than the smallest element in the list, then I put it at the front. Otherwise, I keep the smallest element at the front and try to insert the number somewhere into the rest of the list. Let's check if we actually sort anything. And we're good. Now, my question is, what's the performance of insertion sort of this function? What is the worst case, and how does it perform on that one? Yeah? No? Well, actually, yeah, but we kind of lump it under n squared because of that. Yeah? Exactly. If we have a reverse list, that is definitely the worst case performance for this one, because what we get is we try to sort a reversely ordered list. We need to insert 4 into a sorted version of 3 to 1. Without this first one, right? Then in the next step, we are inserting 3 into a sorted version of 2, 1. In the next step, we are inserting 2 in a sorted version of just 1, which, let's say, will immediately return return the list of 1, right? So at this point, I went through the list n times, right? And at each point, I'm doing an insert. In this case, 4 will be at the end of the list. So again, I'm going through the whole list here. 3 will be at the end of this list, so I'm going through the list here. 2 will be at the end of the list here, so it will be in the list of there. So roughly, we are really performing n factorial steps, but we lump it under n squared, roughly n squared. So that's for the worst case. It turns out that this is roughly also the performance of an average case, right? So on average, actually, and there are proofs for this, insertion sort will always perform like this. In the base case, the best case scenario for insertion sort is a list that's already sorted, right? Because then insert will always return immediately because the lowest element is at the front of the list. So we just need to put the number at the front. So we only go through the list just to check that it's actually sorted. And n in best case, which is already sorted. Now, it's one sorting algorithm. The advantage of insertion sort is really that it's very, very simple, right? It's quite quite easy to implement, and it follows our list template, right? Both of the functions follow the list template, so it's easy, really easy to go from the template to there. Now, we can improve this algorithm by, or get a better sorting algorithm if we think about the properties, or if we think about different ways of splitting up the sorting problem into smaller problems, right? Here again, because we stubbornly followed the list template, what we were doing we were always splitting the problem into one smaller and the extra element, right? Always chipping away one at a time. So there are quite a few other sorting algorithms. The one that I want to look at today as the last thing is one that is called quicksort. Anybody heard about quicksort? Charlie heard about quicksort? I once had dinner with the inventor of that algorithm. Tony Hoare, a British computer scientist, invented this one. So quicksort has the following idea. Take a list of numbers, select a number as something that we call a pivot, the list into two lists. Numbers that are smaller and numbers are then the pivot. Okay. Then sort both lists independently, and finally append the two sub-lists in the middle. Okay, so in the end we get a list of smaller, pivot, bigger. Right? Because smaller already contains everything that's smaller than the pivot, and after sorting, it's a sorted list. That means that everything up to the pivot and including the pivot is now sorted, right? Bigger contains all the elements that are bigger than both smaller and pivot, so it's in its right place. And because it's sorted, that gives us a sorted sequence as a result. And the important thing is here that instead of just taking away a single element, right? We are splitting the list into two sublists, right? And what this gives us is, on the average case, we will, in the best cases actually, we will get to that, we will be splitting the list into two equally sized lists, so the recursive calls are on lists that are half the size, even though we do two of them. Okay, so let's implement this idea. I'll call it qsort, and of number returns a list of number. Fine. L. Okay. So for just like with insertion sort or any other kind of list, what is the trivial case here? Finn? Empty list, exactly. So we need to know when it's time to finish, right? And that is exactly when we have the empty list, right? We're done, nothing to do there. And then we have a non-trivial case, right? When we actually do have some elements, and we actually do want to sort them. So what I said was we want to split the list. So the first thing is that we want to pick a pivot, right? Then we want to get all the elements that are smaller, all the elements that are bigger, right? And then our idea is to simply concatenate the lists after sorting the smaller elements, inserting the pivot in the middle, and sorting the bigger elements. Okay. Now what should we pick as the pivot? Yeah? We can pick the first element. Your guess is as good as mine. There's nothing really special about that one. Now, actually the ideal pivot would be the median of the list. But to get the median of the list, we would already have to have a sorted list, so might as well pick the first one. We just want to pick a random number. How do I get all the smaller elements? Yeah?
So you could have it like, if it's less than pivot, then cause it to like a running list of what's getting added.
If only I had a function that would do exactly that. Finn? Filter. So we want all the ends that are smaller than the pivot to be in the smaller list, right? And because we already picked the pivot, we can just filter the rest of the list, right? We pick the first number, that's our pivot. We'll be inserting it in the middle. So we filter out those, and conversely, all the bigger elements are simply elements that are, or we can also express it like this. Okay, and we're done, almost, yeah? Exactly, good question. So, the way I wrote it is a simplification because it doesn't really take care of the case when we have more than one pivot in the list, right? If pivot is equal to another element of the list, I would now ignore all those elements and remove them from the list. So what we can do is just collect all the ones that are equal to the pivot as another list, and we can no, actually we can do this, and instead of sticking the single pivot, we just stick in all the ones that are equal. Okay. Let me check if we define it correctly. Thank you, Ellie. And the question is, another question online is, does equals include the original pivot though? So because I'm filtering the original list, the first one that will get included is actually the the first one. I could have just as well written it as this. Okay, to make it a little more explicit that the pivot is actually included in that list. Okay. Okay. And this one's quick sort. Let's check that it actually works. Probably a million typos there. No. On the first go, that never happens. Josh? Yeah, exactly. So if we are in the empty case, we cannot take the first, we cannot take the rest, so this would fail. Okay. Make sense otherwise? Okay, so we have a little bit of time. Let's first do the argument of why this function terminates, right? Before, again, it was easy. We used the list template, always smaller elements, so it was okay. Now, here we are always calling the queue sort on just two lists, right? And those are not immediate rests of the list. However, they do return lists that are strictly smaller than the original list. So using this recursive scheme, we will always reduce both of these lists. They will always be at least one smaller, and eventually we'll get to an empty case. So that's why it terminates. And in fact, it would be okay even if we didn't do this, right? That the termination would come from that the filter. The result of the filter is, again, at least one smaller than L, because no number is less than itself, and no number is greater than itself. So the filters wouldn't include those numbers, so there will be at least one element smaller. It's just a slight optimization. And the equals is the only list that has a potential to be exactly the same as the original list, but that we don't use in the recursive call. So we're good, and we terminate. Okay. Now, you can argue that we are doing quite a lot of traversal through the list just by doing those filters, right? But for large enough inputs, all these things that we are performing here actually become quite small compared to the other operations that we do. And moreover, we could join these three calls to filter into a single call that just go through the list and collect three. We would make a struct of three things. Smaller ones, put it there. Bigger one, put it in the third one. Equal, put it in there, and we would just traverse it once, and that would be even better, right? The important thing that we do here is that the recursive call on QSort, although we call it twice, every time we call them, it's on lists that are at least one smaller, right? So we still have, if in the worst case, right, if we would have a list that at each call we would have all the numbers in here and an empty biggers, right, and then one pivot or vice versa, then we would get a performance that is again n squared, and it would perform like insertion sort. Turns out on average you will get a much even distribution between those two lists, right? And in the best case, you actually split, in each call you split the list into two. You perform half of this, you add them together, okay? And the performance characteristic, and I don't want to go into the detail on that because I don't remember all the math and I don't want to lead you astray. and B, it's not really necessary, the performance of this algorithm is actually n times the logarithm to the base 2 of n. Right? This log 2 of n comes from the splitting of these. The n comes from doing this n times, having to go through the list completely, right? Because we pick a pivot and we compare n times. Every number will be a pivot at least once. Okay. So best case and roughly, and worst case still n squared. Okay. So before we finish, I just want to make another observation. This might not be entirely obvious. Even in the worst case, there might be reasons why we want to pick an algorithm like quicksort, right? Even if we know that we are approaching a worst case and we might have the two things. You might not notice that, but once we separated out the smallest and biggest, the two calls to the quicksort are independent. Whenever we have two independent computations, that means we can make use of concurrency, and we can very easily make them run on two separate things. If I'm sorting half of the internet, right, I split the internet in half, sort one half on one cluster, sort one half on the other cluster, and I get a much better performance than trying to pick out thing one by one and inserting it into a sorted version of things like that. So there are several sorting algorithms with different performance characteristics that might have different advantages to your particular use. Right? In a lot of cases, going for insertion sort might be the best thing, because you have small lists, you are going for easily understandable algorithms, etc. You might pick that one. Then quicksort, other very divide and conquer algorithm is called merge sort. You might heard about it, and there are a few more. Okay, so, but the important thing here is that we used our knowledge of the problem, right? The fact that any list can be split into smaller and bigger ones that can be sorted independently and then merged together to get a generative recursive solution to our sorting problem, rather than the kind of naive recursive version that is insertion sort. Are there any questions that I can answer? Any doubts? Okay, so that's it for today. Thank you for coming. Thank you for participating, and I'll see you on Wednesday. Thanks so much.